All right, let's go over these. Example 8, I don't know if we got exactly to example 8 yesterday, but that's where we're going to start today, and then we'll backtrack if we need to. So we have this function here. This is called a rational function. It's just a ratio of two polynomials. You got a quadratic over a linear, and of course there's no radical for these types of functions. So if we were to find the domain, which is what we kind of always want to get in the habit of doing first as we encounter functions throughout the year, you might be able just to rattle it off without showing the analysis. And something like this, it would be okay if you don't actually show the whole analysis. We're working towards being that efficient. What's the only value of x that's not in the domain? 2, right? Because x minus 2, the entire denominator can't be 0. If you solve, you get x can't be 2. And that's it. There's no radical, so that's it. So what that means, again, the consequence is that the graph of f of x lives to the left of 2 and to the right of 2, but not at 2. So 2 interrupts the flow of the graph from left to right, and therefore we say that x equals 2 is a discontinuity. It interrupts the flow of the graph of f of x. And that's just a generic term. It's a very broad category. Yesterday we talked about two types of discontinuities, right? What were they? Holes and vertical asymptotes. What was the official name of a hole? A removable point discontinuity. It was a single ordered pair xy that was swiped out. And what made it removable, again, is that if I gave you a tiny little manhole cover, you could walk up to the hole and you could put down the single manhole and make the graph continuous again. That's what makes it removable. As opposed to a vertical asymptote, which has a proper name of what? Non-removable infinite discontinuity. Infinite because it forces the y values either up or down to infinity or negative infinity. And non-removable because you cannot take a little manhole and put it down on that vertical asymptote and make the two graphs connect. It's what makes it non-removable. And then we said, okay, there was a way from the equation to determine for any discontinuity which of those two types it was. And what was that? Factor, yeah. If we can factor the numerator doesn't tell us which discontinuities we have, that's the denominator. But if I take the whole thing together, I can determine which type each discontinuity is. So, did anyone successfully factor the numerator? 2x minus 1 and x minus 2. Good. All over x minus 2. So because the x minus 2 factors, as you can see here, they divide out, we could then say that, what? F of x has a hole, and you can use the word hole, at x equals 2. That would be correct, at x equals 2. But we could do better than that. Remember, the hole is called a removable point discontinuity, which implies there used to be an ordered pair. They didn't just take an x value from us when they swiped it away. They took the y value too. So I'm going to show you very quickly how to find the y value. If this was just an expression and not a function, then the expression that we had originally, 2x squared minus 5x plus 2 over x minus 2, would be equivalent to the expression 2x minus 1, right? Because the x minus 2's divide out. Well, the only difference is when it's a function now, we can still simplify the expression that is a function, but we'll have to make a little warning label at the back. Hey, don't use 2. Because here's what's cool. The graph of f of x looks exactly like the graph of 2x minus 1. They're equivalent expressions. They're only not equal at 2. Okay, that's the only point where they're not the same. Everywhere else, they look exactly the same. So you can imagine that the function before the hole was swiped looked like the function 2x minus 1. What does the graph of 2x minus 1 look like? Well, that's easy, right? It's down 1 unit for the y-intercept, and then it's up 2 over 1 for another point. And if we connect those 2 points, that's the graph of 2x minus 1. What's the difference between that and the graph of f of x? Well, f of x apparently at x equals 2, if I go up where the graph is, I'll just put an open circle there. That's what the graph of f of x looks like. So, if I'm interested in what the y value is of the hole, how could I use the 2x minus 1, which is what the graph looked like before the hole was taken out? How could I use that equation to find the y value of the hole? Plug in a 2 for x, yeah. So if I plug in a 2 for x, I get 2 times 2 minus 1, and I guess I should call this g of x, not f of x, because it's different. So then I can call that g of 2. That'd be 4 minus 1, which is 3. Okay? And that is actually the coordinate of the hole. So instead of saying f of x has a hole at x equals 2, we could do better now and say f of x has a hole at the ordered pair 2, 3. And there you go. So let's review. How did we find, first of all, the fact that there was a general discontinuity at x equals 2? What caused that? Well, the fact that 2 made the denominator 0 meant that it was a discontinuity. How do we decide it was a hole? Well, it factored out. Okay, we were able to remove it from the equation. How did we then find the y value of the hole? We plugged that 2 into the simplified version. If you know you have a hole, if you get rid of the factor that's causing the hole, you can plug that value into what's left over, the simplified version after it's gone, and that gives you the y value of the hole. It's that easy, okay? Now, you could figure out that there was a hole there without having to factor, and here's how. I know that if I would have plugged in a 2 in the beginning, f of 2, into the original function, I know totally I would have gotten a 0 in the bottom. What would we have gotten in the top if we plugged in the 2? Well, you can plug in a 2 here. Let's try it. 2 squared is 4 times 2 is 8. 8 minus 10 is negative 2. Plus 2 is 0. Or you can look at this here. This would be a little bit easier, right? If you plug in a 2 and there's a hole, you're going to get 0 over 0. And here's an easy way to remember. 0 over 0 is hole. 2 holes, right? Is a hole. The reason that it's removable is because there's a factor of x minus 2 in the top and bottom. Well, if there's a factor of x minus 2 in the top and the bottom, then when you plug a 2 into the top and the bottom, that x minus 2 factor is going to cause a 0 in both the top and bottom. So now you have 2 ways to determine if an x value is a hole. You either completely factor it, which is not always easy, right? Sometimes it's tough to factor. And if they divide out, it's a hole. Or you can now just take that same value and plug it into the top. If you also get a 0 in the top, 0 over 0 also means a hole. Now, the only bad part about knowing it's a hole from plugging in is you would still need to then factor it so that you could simplify it to figure out what the y value of the hole is. But you might be able to just figure out there's a hole by plugging in without having to factor. All right, that makes sense? Okay. Let's go to the next one here. It looks kind of similar, but it also looks kind of different. This one's g of x. Let's find the domain first. What's the domain of g? Again, you don't have to show all the analysis. Instead of all x, I said x ain't 2. That's the only value that makes the denominator 0. The graph lives to the left of 2 and to the right of 2. So x equals 2 is a discontinuity for sure. It's a discontinuity. Now, to figure out what type it is, we could either try to factor the top and see if the x minus 2 does or doesn't divide out. Let's try our new trick, though. Let's try out our new trick. I know that when I plug in a 2 for x in the denominator, I get 0. So g of 2 is going to be something over 0. Let's see what I get when I plug it into the top. If I plug a 2 into the top and I get 0 also, then there's another hole at x equals 2. What do I get? 2 squared is 4 times 2 is 8. 8 plus 6 is 14. Minus 2 is 12. I get 12 over 0. If I plug a 2 into the top and get 12, does that mean x minus 2 is a factor of the numerator? No. No. And since I did not get 0 in the top, x minus 2 is not a factor in the numerator, will I then be able to factor out an x minus 2? No. So the x minus 2 will be non-removable. Therefore, what? Very good. It's the other one. G of x has a VA, a vertical asymptote, which is, again, an infinite non-removable discontinuity, at x equals 2. Is there an ordered pair associated with a vertical asymptote? No. It runs north and south forever. So we have a way now to determine by plugging in, not just our ability to factor, if something is a vertical asymptote or a hole. If you plug in and you get any non-zero number over 0, like 12 over 0, 5 over 0, 17 over 0, that means that the number you plugged in is not a root of the numerator, and x minus that number is not a factor. It's non-removable. So any non-zero over 0 when you plug in means vertical asymptote there. And over here, anytime you get 0 over 0 when you plug in, it is a common factor that will divide out. You're going to have a hole. Okay? 2 ways now. Factor, divide out or not divide out, or plug in. 0 over 0 or non-zero over 0. If we were trying to factor the top as x minus 2 times something, would we have been successful? No, it wouldn't factor in x minus 2 times something. Did anybody happen to factor it? Did it factor? It did? What'd you get, Miss Wilson? 2x minus 1 and x plus 2. Let's see what that is. That gives us a 2x squared. Then we got a 4x minus 1 is plus 3 and a minus 2. Perfect. So it did factor. Do the x minus 2 factors divide out? Nah. Okay, so again, you can kind of see that when you plug a 2 into the top, you will not get 0 because there is no x minus 2 factor in the top. So non-zero over 0. So plugging in can be useful if you're trying to find vertical asymptotes. Any non-zero number over 0 is a vertical asymptote. All right, let's try Texas of x. Again, you probably don't need to show the analysis here. The domain of T will be the set of all x such that x ain't what, y'all? Negative 2 and positive 2, don't forget the plus or minus. You can list them as conjugate pairs. So, are 2 and negative 2 discontinuities? Yes. Any value that makes the denominator 0 is a discontinuity. The graph lives on either side of both of those values. Those two x values interrupt the flow of the graph. Now to determine which type they are. How do you want to do it? You want to try and factor, or you just want to plug in? If you said factor, factor. If you said plug in, plug in. Bleh. Sometimes one's easier than the other. I think I'm going to factor here. Factoring is not always easy or possible. But I know the bottom's the difference of squares. So x minus 2, x plus 2. And the bottom, the top, the leading coefficient is 1. So if it factors, it's going to be the easier variety. Factors of negative 12 that give us negative 4 would be x minus 6, x plus 2. I think we have the answer now for both of them, right? The x plus 2 factors divide out. They divide out. So what's the x value associated with x plus 2? That makes it 0? Negative 2. Very good. So T of x, T of x has a what at negative 2? Has a hole. If you can remove it from the equation, it's a removable point, discontinuity, or a hole. Has a hole at, and let's go ahead and list the ordered pair. Negative 2, comma, how do we find the associated y value of the aforementioned hole? Plug a negative 2 into what's left over, the simplified version, which I boxed for convenience. Let's do this together. Negative 2 minus 6, negative 8. Negative 2 minus 2, negative 4. Negative 8 over negative 4, positive 2. Yep. In fact, the function t of x looks exactly like the graph of x minus 6 over x minus 2, except the graph of t of x has a hole at negative 2 over 2. Other than that, they're exactly the same. Now, the other factor in the denominator that causes 0, x minus 2, does not divide out. There is no x minus 2 factor in the top, so it's a non-removable factor, and its x value is a non-removable infinite discontinuity. So t of x has a VA, you could say VA, that's fine, at what? X equals 2. It's not an ordered pair, it's actually a vertical line. The equation of a vertical line is x equals. So you have to say x equals 2. Don't just say a vertical asymptote at 2. 2 what? Oh, x equals 2. And don't say y equals 2, because that's a horizontal line at x equals 2. All right. That's it for now. Pretty easy, yes? Okay. So let's summarize then our new little trick. We can factor always to decide, or if we plug in and get 0 over 0, it's a hole, or a hole, if you want to do that, 2 O's. If you plug in and get non-zero over 0, any non-zero over 0, then there's a VA, a vertical asymptote there. And then the other one that is worth mentioning, since we're talking about zeros, is the third one. If you plug in and get 0 over non-zero, then there's no discontinuity at that x value at all, right? Because the answer is 0. Okay? Non-zero in the denominator is not a discontinuity. But 0 divided by anything that's not 0 is, in fact, 0. So really the two that we're looking for in terms of discontinuities are, again, the ones that give us a 0 in the denominator. Those are the discontinuity values of x. Okay? There's practice problems on the worksheet for doing that. Sometimes factoring is more fun on one problem than it is on another, but we spend a lot of time on factoring. So I'll let you try those. Any questions on how to decide if it's a whole or a vertical asymptote? Those are the two main types that we're going to study later on. We'll have a whole unit on these types of functions. These are called rational functions, and the discontinuities are just one aspect that are going to help us sketch the graphs without the calculator. All right, there is a third kind that we'll encounter throughout the year, and it's another non-removable type. It's called a jump discontinuity, and it's a non-removable type, which means what? What does non-removable mean again? Yeah, you can't factor it out, but in terms of the graph, if I gave you a tiny little manhole cover, you can't place it down to connect the graphs like you can for the only removable discontinuity, which is the hole. Okay? I'm going to skip example 9 and come back to it. If I was to redo these notes, which I probably will for next year, I would put example 10 ahead of example 9. So, let's look at example 10. And let me clear off this sheet down here first so that we don't see the answers. All right. Example 10, these are called piecewise functions. We're going to state the domain and range after we graph it, and then we're going to talk about any discontinuity. So you might have had limited experience with the piecewise function. But man, you could see them coming a mile away, because here's what they look like. F of x equals, you have the open brace, like it's going to list a set of things. But it's not a set at all because there is no closed brace. So if you see a set notation that's only open, and you see these different pieces in here, that's why it's a piecewise function, defined over different intervals, that's what this is over here, you've got yourself a piecewise function. So let's look at it a little more closely. This says everywhere to the left of 0 and at 0, less than or equal to 0, the graph looks just like the line x minus 1. But at 0 then it changes, and everywhere to the right of 0 but not including 0, it resembles the graph of x squared. So it's still a function because there's no overlapping x intervals, right? That would violate the rule of a function. So if you look at the two pieces themselves, x minus 1, if you were just to graph that by itself, would it have any discontinuities? No, that's your 45-degree sloping line with the y-intercept of -1. It's continuous everywhere. And then x squared, your happy parabola, if you were just to graph that, would it have any discontinuities? No, it's continuous everywhere. So the only place where this piecewise function might be not continuous or might be discontinuous is at what x value? 0. Because you can think this is kind of like a relay race. X minus 1 is running the race from negative infinity, don't ask me where he lines up to start the race, all the way up to 0 and including 0. And then at 0, he hands the stylus or the baton to the graph of x squared, who then has the race to run for the rest of eternity, to the right of 0 forever and ever. The question is, are they standing at the same y value at x equals 0 so that they make a smooth baton exchange, or do they drop the baton? We shall see. You might already know the answer. So here's how I sketch piecewise functions. 0 is kind of what we're interested in. In fact, 0 is the most interesting value of x on this function because it's where the baton exchange happens. All right, so draw a little y-axis, a little x-axis, and of course, 0 we don't have to mark. We know where it's at. I always do these graphs from left to right, which is usually the top piece and the bottom piece. I know that at 0 and to the left of 0, it's line x minus 1. I want to know where this graph ends up at 0. I want to know what the y value is at 0. So I'm just going to take 0 and plug it into this first piece for x. What do we get? -1. Now, because there's an equal sign there, I will put a solid dot at the point 0, -1. Solid dot. Now I will complete that graph so I don't forget what I'm doing here. It is a graph of x minus 1. I know it's a line. If you want to pick any other point to the left of 0 and find the y value there, you can plot it and then connect the dots. But I'm not going to be that picky. As long as you have the slope right, I know the slope is +1, right? So if you just come to the left of 0 and just draw a line that kind of resembles the slope of 1. Up 1 over 1, up 1 over your 45-degree line, and put an arrow at the end. That's it. That's all you have to do. If your slope is 4 or 3 or 1.5, it's all good. If it's negative, though, Okay, so that's where that function ends up. Now, at 0, x squared picks up. I want to do the same thing. I want to know where x squared starts. I want to know where x minus 1 ended, and I want to know the y value where x squared starts. So I will also plug a 0 into x squared, and what do I get? It's okay. 0 squared, I get 0. Now, at the point 0, 0, do I put 1 solid dot or 1 open circle? I have to put an open circle because there's no equal to. And that's how we would graph it. Okay, it's an open circle. Now, to the right of 0, it's going to look like x squared. That would have been the vertex of x squared, right? But now I only draw it going from that point and to the right. So something that would resemble x squared. And we put an arrow on the end. Whether we shade it in or not, that's up to you. But guess what? Voila! We have the graph of the piecewise function. And does it pass the vertical line test? Yeah, it sure does. That wasn't difficult at all. Let's find the domain now. What would be the domain of that function? All real numbers. Every single x value has a y value associated with it. The range is a little more interesting. We don't get anything between -1 and 0, right? So let's list this as an interval. I think it's easier to list it as an interval. So from low to high, what y value do we start at? -infinity, which always gets a parenthesis, right? Up to y equals -1, bracket or parenthesis? Bracket. We include it. Union, parenthesis, y equals 0, and then all the y values go up forever, so infinity. Very good. That's the range. Okay, now, if we were to sketch this function truly from left to right, could I do it without lifting my stylus? Nope. I would have to start over here on the left, and when I got to the point 0, -1, I would have to leap from y equals -1 to y equals 0 to continue on my journey from left to right. Leap is not a bad word, but maybe a better word would be jump. Yeah, very good. This is not a vertical asymptote, right? There is a discontinuity at 0, obviously. There's a discontinuity at x equals 0, okay, because the graph's not connected there. Discontinuity. But it's not a vertical asymptote because the y values aren't going to infinity. And although there is a hole at the origin, is this a removable discontinuity? I already have a manhole cover down at x equals 0, right? Is there a way to pick up the little manhole cover at 0, -1 and move it to a different place to make the two lines touch and connect? So it's non-removable, so it can't be a hole. The hole is the only one that's removable. So even though there looks like there's a hole, it's not a hole. This is, in fact, a non-removable jump. So we would say that f of x has a, and you could just say jump if you want. We know jumps and vertical asymptotes are non-removable. At what? At 0, -1, or 0, 0, or just at x equals 0? At 0, 0? Right, very good. Yeah, I set you up to answer that one. That wasn't fair. At x, you said it right the first time. At x equals 0. It's not an ordered pair. There's actually two things going on there. You don't list them both. Just at x equals 0, there's a jump. So anytime the graph is approaching two different y values from either side of an x value, not infinity, but two distinct y values that actually exist from either side, you know, like if you're trying to make your fingers match up and one eye's closed, right? Sometimes it doesn't always work. Have y'all tried that lately? Close one eye, do your fingers match up? If they do, you're good. But if not, you just have made a jump discontinuity, right? Okay, whatever. Yeah, it is fun. Try it with the other eye. You can figure out what your dominant eye is. You know, if you close one eye and they move dramatically, then you've identified your dominant eye. You know how someone identifies their dominant foot? You come behind them, you push them real hard. Yeah, whatever foot they catch them, so it's like, oh, your right foot dominant. Thanks a lot, jerk. Yeah, that would just be slow reactions. Oh my gosh. Okay, any questions on number 10? We have a jump. Jump discontinuities normally come from piecewise functions. You don't encounter jump discontinuities in the rational functions that we saw in the previous example, where it was just a polynomial over polynomial. They come from piecewise functions, normally. There are a couple of exceptions. Okay, letter B. Boy, it looks very similar, but it is a little bit different. It is a piecewise function, right? I don't have to remind you why. It has that very telltale look, very characteristic look. To review how to sketch it, 0 is where they're trading. Oh, by the way, did they make a smooth baton exchange? No, they didn't coordinate it right. I guess they had to throw the baton. I don't even know if the other guy caught it. So, okay, we won't even bring that analogy up on this problem. I want to know where the x minus 1 ends. Everywhere to the left of 0, it's x minus 1. I can plug in a 0 to x on the top piece and get -1, except this time, because it's strictly less than, I put one solid dot or one open circle? Open circle. And then everywhere to the left, make sure you're sketching on the correct side. To the left of 0, it's the line with the slope of 1, so we'll just draw it going up to that point. And then to the right of 0, it starts at 0, 0 with an open circle, and it looks like that. Very similar. Very similar. What's the domain of this one? What? Can't be 0? Yeah, very good. The set of all x such that x is not 0. Now, the fact that it can't be 0 has nothing to do with the two pieces themselves. The two pieces are continuous on the open intervals where they're defined. This one is explicitly not defined at 0. In the definition on the right side that tells us which x values to use, it does not include 0. Okay? Did that affect the range at all from the previous example? Yeah, it did, slightly, but enough that it's worth redoing. Negative infinity now up to -1, non-inclusive. Union 0 to infinity. We can't include the y value of -1 anymore. Is it continuous for all real numbers? Or is there a discontinuity somewhere? There's a discontinuity. What type is it now? Now if there's no dot, is it a hole? No, it doesn't make it a hole. The only way it would ever be a hole, even though it looks like there's two holes, right? You think it's extra holy, is if you can get one manhole cover and put it down at one place and make the two lines connect. You can't do that. So this is still a jump. So we still have a jump at x equals 0. All right. Any symmetry on this function? Y-axis origin? Nah, none. Okay. Questions on that? Very similar, but different. All right, this was also very similar. This is a three-headed bunny or cat or monster. Not that bad. It's not a monster. Three-headed cat. Three-headed kitty. It's cute, but it has 3 heads, but it's cute. It's odd, but it's nothing to fear. Okay? All right, so again, to the left of 0, it's x minus 1. I want to know where that graph terminates. So I'll plug in a 0, and I get negative 1 once again. But because there's no equal sign, I put 1 open circle. And now to the left, I know it's the slope of 1, so just like we've done before, like that. Now notice the middle piece here. It says, when x is 0, y is 1. That's a little dot at the point 0, 1. That couldn't be more explicit. Got it. One little dot. And of course, I made my dot not true to size, right? I made it big to enhance the texture. Now, to the right of 0, it's x squared. If I plug in a 0 for x to see where it starts, surprise, surprise, it starts at the origin, and it looks like that. What's the domain? It's back to all real numbers. Every x value now is defined to be one y value. What's the range? Is it the same as the last or same as the first? All reals, the range? So we get negative 1/2 somewhere? The domain's all reals. Well, when in doubt, just scan your graph from low to high. We still start at negative infinity, and then we stop right here at y equals negative 1, which we don't include. Union. We start right back at 0 non-inclusive. And do we get all the y values greater than 0? At least once? Are you allowed to get y values twice? Think of x squared. Every y value except 0 occurs twice, right? For the range, for a y value to be included in the range, it has to occur at least once. So notice that the y value of 1, it actually occurs twice, which is okay so long as it comes from 2 separate x's. And it does. So it's still 0 to infinity. So it is the exact same range as the previous problem. You can have y values repeating, that's fine, as long as they come from a different x. And these do. Discontinuity now. Is it still a jump? Or is it now something else? Still a jump. It's a jump at x equals 0. The only one that's an ordered pair is the only one that's removable, and that's the whole. All right, last one. Woohoo! Back to a 2-headed, whatever, bunny, cat. Okay, let's graph it. We got an x and y axis to draw first. 0 is still the point of exchange, so I'll plug a 0 into there, and I get negative 1. But now because the equal sign has returned, I can put a closed dot. And still a slope of 1 coming up to there. So that one's getting pretty routine. Now the next one is just to the right of 0. If I plug in a 0 to see where it starts, though, I get 0 squared, which is 0, minus 1 is negative 1. Because there's no equal sign, I have to put an open circle. How do I put an open circle at 0, negative 1 if there's already a stupid closed circle in the way? Oh, yeah, let's put an open circle around it. Nice. That makes the dot a little bigger, which is not bad at all. And then x squared minus 1, the minus 1 moves your graph of x squared down 1, so now it looks kind of like that. What's the domain? All real numbers. What's the range? All real numbers. Any discontinuities? Jumps, holes, vertical asymptotes? No discontinuities. This graph is continuous over its entire domain of all real numbers. That's pretty cool. So just because you have a piecewise function doesn't mean they're going to mess up the baton exchange, to return to that analogy. Sometimes they actually exchange it properly. So going back to the beginning then, since it is continuous at the point of exchange, would it have made any difference to the function if I would have gotten rid of the equal sign from the top and instead had it down here on the bottom? Would the graph look any different? No. Okay, they can fight over who gets to claim it, right? Now, with that in mind, could I then also have the equal sign up top? Could I have the equal sign on both of them? Would that still be a function? The graph would still be a function, but there's different ways to represent a function, and none of them can have a sharing violation. So although graphically it's inconsequential to have a sharing violation in this case, this is still a sharing violation. You say when x is 0, it's this piece, and when x is 0, it's that piece. So technically, no, that's bad. Only one of them can claim it. If they happen to be the same, let them fight over it, right? When they're done with the relay race, which is never, have them fight over it. Something else to watch. Okay? Only one of them can claim it in the function. All right, any questions on piecewise functions? Kind of fun, right? As a teacher, I really like them because 2-for-1 deal, right? And as students, you like a bargain. You like real value. So you like the 2-for-1 deal too. Or the 3-for-1 deal. Okay, let's jump back up then to example 9. Example 9 looks kind of like the one from example 8, right? Because now it's a quotient of two functions. And it doesn't look like example 10 because there's no brace, so it doesn't look like a piecewise function. But it is different because in the numerator you notice it has the mark. It has absolute value signs. Yeah. Okay, let's go ahead and first of all determine what the domain is of the function. Because that's what we want to generally get in the habit of doing first and foremost. You don't want to talk about a function where it doesn't exist. There's no radical, but there is a denominator. What's the only value that gives you division by 0? 3. So, it's a set of all x such that x ain't 3. Now, because it's a ratio, we learned up above that there were little tricks, right, for plugging in to determine which type it was. So let's do that here. F of 3 yields, of course, a 0 in the denominator. But what does it yield in the numerator? Go on, don't be shy. You get an absolute value of 0, right? Which is what? 0. Sweet. So up above, when you plugged in, you got 0 over 0. 0 over 0 meant that discontinuity was a whole, right? Remember the little H up here in the LE? Whole. Well, guess what? This is the exception to the 0 over 0 being a whole rule, okay? And it's going to be pretty easy to spot the exception to the 0 over 0 being a whole rule because it's going to have the mark, okay? It's going to have absolute values. Now, I will show you why it is not a whole. If it doesn't have the mark, if it was just 5x minus 15 over x minus 3, it would have been a whole at x equals 3, faux show. But it's not, and here's why. We can actually rewrite this function as a piecewise function. The absolute value over a function is a piecewise function in disguise. Here's why. If we were writing a computer program that would basically perform the operation of taking the absolute value of something, we would have to tell the computer what to do when it saw the absolute value signs. Okay? So when you're creating a piecewise function, that's kind of what you're doing. So I know it's going to be x minus 3 in the denominator on my first piece. But here's what I want to consider. For a certain value of x, when I plug them into my numerator up here, 5x minus 15, for certain x values, I'm going to get a positive number already in the absolute value signs, right? Like what? If I plug in a 4 for x into the top, what do I get? I get 20 minus 15, which is positive 5. What's the absolute value of positive 5? 5. So I don't need to do anything to it if it's already positive. What if I plug in like a 6? Will it still be positive in the top? Yeah, I get 30 minus 15, it's positive 15. So I want to tell the computer, hey, if the thing inside the absolute values is already positive, just drop the absolute values and take that number as it is. Well, I need to figure out for what x values 5x minus 15 is positive. I need to figure out for what x values 5x minus 15 is positive. greater than 0, greater than 3? Yeah, it might be intuitive to some of y'all, right? But if not, here's how you could do it. 5x minus 15 greater than 0. That means positive, right? I've just set up a little linear equation which we can solve algebraically. So 5x would have to be greater than 15. And as JC already pointed out, that means x is greater than 3. So here we go. When I put a comma here, I'm going to say when x is greater than 3. That's kind of like the if command on a computer program. If x is greater than 3, then, and now we tell the computer what to do, then drop the absolute values and take it to be 5x minus 15. Does that make sense? If you've had any experience with computer programming, depending on the language, what's that? That's your next class. Okay? Else, there used to be a command called else, which means if it's not greater than 3, it's less than 3. We would have to take the opposite of it. Anyway, this one is not going to be critical to the notes. We'll finish this one some other time. The worksheet's still due tomorrow. This actually turns into a piecewise function. So have a great assembly while you're taking your quiz, yeah. So you either have your iPad open or your paper out. Yeah, you don't have to submit it to eBackpack. Actually, those of you who are left, let's finish it. Yeah? That it didn't? Since I'm still recording, we might as well get the full effect here, huh? Yeah. All right, so for those of y'all who are still here, what happens next is that we can simplify this piecewise function. And I'll try and make it quick. I don't want to, give y'all bonus math. Y'all feel like y'all probably don't deserve it. If I try to simplify now, notice in the numerator, in the first row, I can factor out a 5. So I get 5x minus 3 all over x minus 3. Well, what happens with your x minus 3's now? They would divide out, right? And I'm just left with 5. So as it turns out, that original expression, for any value that was greater than 3 that you plugged in, you always got a 5. And we could verify very quickly. By coming back up here, let's see what happens when I plug in a 4 to the beginning. I would get 20 minus 15, which is 5, over 4 minus 3, which is 1. 5 over 1 is 5. If I plugged in a 6, in the top I would get 30 minus 15, which is 15, over 6 minus 3 is 3. 15 divided by 3 is 5. So you're going to get a 5 every single time. Similarly, in the bottom, if we factor out a 5 and join it with the negative out there, you're going to get x minus 3 over x minus 3. Those will also divide out, and you're left with negative 5 when x is less than 3. So if you want to verify, plug in any value to the left of 3, you're going to get negative 5 each and every time. Now notice that it's not defined at 3, and we already said y at the top. It's not in the domain. But notice what we have essentially done, and I think it's worth rewriting. We now have a piecewise function. F of x is going to be 5 when x is greater than 3, and negative 5 when x is less than 3. Well, that's a pretty easy piecewise function to sketch. We've got our x and y axis here. The point of exchange is going to be at x equals 3. And let's graph it. To the right of 3, it's the y value 5. What does the graph of y equals 5 look like? It's a horizontal flat line, right? So I'm just going to mark that as 5 up there. It's an open circle because it can't equal it, but then I just draw that to the right. So everywhere to the right of 3, the y value is 5. And then symmetrically down here, that's a negative 5. An open circle at the point 3, negative 5. And now I draw it going to the left. And there is the graph of that original function. So 0 over 0 was not a whole. Rather, at x equals 3, what type of discontinuity do we have? Is that removable or non-removable? Can you put a manhole cover down at x equals 3 and make those two horizontal lines touch? Nope. So it's non-removable. There's only two types of non-removable. Is it infinite? Is it a VA? Nope. It is, in fact, a what? It's a jump. Yeah. It's a jump at x equals 3. So here's what you do. In the future, if it looks like a rational function, it's a ratio of two functions, and one of them has an absolute value, if one of them has the mark. And you'll see in the notes that you'll have an example where the absolute value is in the denominator. It doesn't matter where the absolute value is. This could have been 5x minus 15 over the absolute value of x minus 3. As long as one of them has the absolute value and the other one doesn't, then one of them is always going to be positive and the other one is going to be positive or negative, which is what causes that symmetrical y value, in this case of 5 and negative 5. If you have an equation like that, a function like that, and you get 0 over 0, this is the exception to the whole rule, it will always be a jump at the value of x that causes the 0 over 0. That's the singular exception to the 0 over 0 rule. If one of them has an absolute value, there will be a jump there, not a hole.
Would we have to show the work?
You would not have to show the work. Yeah, you would not have to show the work. You could always break it down into a piecewise and see it, but at this point, I'm not going to have you break it down and graph it. If you go on to take calculus later on, this type of function will be very important. So if you want, let's look at one example from, well, let me make up an example that you might find in the notes, since we just saw that, and we'll practice it real quickly here. If I give you f of x, let me zoom in a little bit. If I gave you f of x equals, let's see, we had it in the top last time, so how about 3x, let's do 4x, 4x plus 20 over 5x plus 25, and I put absolute values around the bottom. Okay, that has that characteristic look to it, right, where it has the mark right there. It happens to be in the bottom. Let's find the domain first. Okay, for the domain, we can't be dividing by 0. So if there's absolute values there, it's not really going to affect our answer. We know that 5x plus 25 can't be 0, right? Because if it is 0, then the absolute value of 0 is 0. So if I solve that, I get 5x then cannot be negative 25, and x can't be negative 5. So there you go. The domain is going to be the set of all x such that x cannot equal negative 5. And because the graph lives to the left and right of negative 5, that's a discontinuity. Now, you suspect that there's a jump there because it has the mark. But let's just make sure. What is f of negative 5? Plug it into the top. What do you get? You get 0. Plug it into the bottom. You get 0. Because you get 0 over 0, and it has the mark, now you could just say, there we go. Now you can say that f of x has a what? A jump at x equals negative 5. So you don't have to do the work. We just did the work so you could see why. But now if you just identify it, you got to make sure it's giving 0 over 0. Because if the top had been 4x plus 21, you would have got non-0 over 0, and the graph's totally different. Now it's the vertical asymptote. Non-0 over 0 always means vertical asymptote. But if it's 0 over 0, it's not a hole, it's a jump. Going back to the problems that we saw up here on example 8, if you don't see an absolute value on either the top or bottom, 0 over 0 then means hole. And that is the whole lesson. We are done with 2.1 already. We're done.